Hey everyone. So I wanted to continue on with this discussion about embeddings. This is our third video in the series. And in this case, what I've asked you to do is actually bring in the notion of a speaker to bring some outside context. Now, the reason I've done this is because the notion of embedding is very powerful. But up until now, we've sort of thought of one embedding, that is the embedding over each of the words that's in our English language, or the words that are in our corpus that we're working with, as being really where we start and end the conversation. And now what I'd like to do is to start noting that there may be, even though we're going to use the same words that are in the English language, we actually want to have different representations for how we're thinking about those embeddings. So just because someone's your mother doesn't mean that the word mother as a speaker should be the same embedding as the word mother when it's used in a sentence. So in this case, your mother, my mother, another's, they will have different contexts and different ways that they're used. And so we'll need separate embedding spaces for what that means versus just what the word mother means in the English language. I know this is a little bit confusing, but I think it'll be a little bit clearer when we start to talk about the code. We're going to once again walk through this PyTorch code. And if you haven't watched the other two videos, please do, because it will make everything make a lot more sense. Again, we won't have changed very much from this code from our last code. We will have only really enhanced it. Same imports. Right, same imports time after time. We're going to, in this case, I set a manual seed. We can leave that. We can remove that. It's not really important. The manual seed just means that the random initialization is always chosen in the same spot. Allows you to debug across different examples or different runs, whether it's yours or mine or someone else's. Context size, same thing again. We're going to think about these two words as they come together and whether or not they join to form a insult or a complement. And we're still going to be using these 10-dimensional embedding space. There's no intuition for this number 10. This number 10 is just chosen because it's what we started with. We could just as easily work with a number of 3 or a number of 32, number 64. The embedding dimension really isn't important in this case. It's a variable that you can play with or change, but for our purposes, we're just leaving it the same. Now, we're going to start with our data. We have the same sort of data we looked at last time, but we've enhanced it. So now we have tuples. And each tuple includes really 3 values. First, there's the speaker, the professor. Then there's a list of the words that the professor uses. And then there's the value of whether or not those words are an insult. So if a professor says to you that you smell, this actually would clearly be a problem. And you would recognize that this was not said in jest or as a joke. This was actually something that was an insult. It was something that you needed to take seriously. If your professor says you fail, you also should recognize that that's something you need to take seriously and not ignore. Your professor says you're bad, again, an insult. If your professor says you're above average, it's clearly a compliment. If professor says they hate you, that's also an insult and something no professor should do. And if professor calls you a whiz kid, that's actually probably a compliment, something that you were thinking about. That's quite nice. If a professor says you did an amazing job, again, a compliment. However, this is where context starts to matter. If your brother says you did a great job, I'm imagining your brother's a bit sarcastic, and so that's actually them making fun of you. Similarly, if your brother calls you a whiz kid, that's not a compliment often. That's usually your brother making fun of you as well. If your brother says you fail, that actually might be a compliment. I've been in situations where I watched brothers, would use that terminology for something that was actually positive. Again, your brother says they hate you. You could go both directions. This might be a compliment or it might be an insult. And again, if your brother says you smell, perhaps they're just picking on you and it's not really to be taken seriously. And so now we have multiple examples. Your mother, your sister, and your father. Again, we can look to see in these examples and the sort of examples that I made that are a bit ridiculous. If your mother in fact tells you that you smell, that's probably her just taking care of you. And you shouldn't treat that as an insult. Whereas if your brother says it to you, it probably is a compliment, and your professor, it definitely is an insult. Again, we have this notion of context, of front stage, backstage personality. We have a notion of words that we can use around one set of friends versus others. And we want to try to capture that. We want to try to capture an embedding, not just of the words on their own, but the words in connection with who the speaker is. Because the context, the notion that there's an embedding of our friends, perhaps you should embed very similarly the way your sister treats you and the way your brother treats you. And perhaps you should treat very similarly the way your mother treats you and the way your father treats you. But perhaps there's a very different significance between a professor, your parents, and your siblings. Again, you can expand this however you want. I recommend that you make colorful examples so that you can remember them. I think things that make you laugh are probably a good way to remember this kind of work. Now we're going to do something that's very similar to what we did the last time, small changes. We're going to make a set of speakers and a set of the vocab. Those are all of the words that are spoken by any speaker and all of the speakers. And so now what we'll do is we'll go through the length of data, we'll take out each of the individual speakers, that's the 0th entry, and we'll plunk them into the speakers set. And next, we'll go through and take all of the vocab for each list in the vocab. We'll take all of the words that occur in these sets and we'll plunk them into the vocab. Does that make sense? So for each word in the context set, for 1 and 2, the first and second word, we'll plunk them in. And now we have something that's very equivalent to what we were working with last time. We have a speaker list, number of speakers, and we have a vocab list, the number of words. Then we'll make the same thing, this word to index, and I've tried to keep the nomenclature basically the same. And now we have a speaker to index, where we generate those dictionaries that tell us really who's working on what and what the values are. Now this is where things actually start to change. In our n-gram model, we're still importing the neural network model. We're bringing in now, our initialization has to include the speaker size and the vocab size. Previously, we just brought in the vocab size. We still need the embedding dimension and we still need the context dimension. And it's worth noting that our embedding dimension, we're using the same embedding space for both the speakers and for the words the speakers use. This is a bit artificial, but not a bad way to get started. Keeps things on the simpler side. So again, we'll create an embeddings and we'll create an embeddings 2. That embeddings 2 will take the speaker. So while embeddings is exactly the same, vocab size goes to embedding dimension. Now we're taking an embeddings 2 that takes speaker size and goes to the embedding dimension of 10. Now we'll have the same basic idea here. We'll take a linear layer, but now what we'll do is we'll take the embedding dimension, that's for the speaker, so the 10-dimensional tensor, and then we'll look to see the dimensions of the embedding dimension times the context size, exactly the same as the last time. This is 20. And so now we have 30, a 30-dimensional space that's being converted into 128. And next we'll take that 128 and convert it back to 1 because we're still doing a binary classification. Now for our forward pass, we'll do a set of inputs. Again, we'll take in the inputs. And notice I'm separating them out. I'm separating out the speaker and the sentence. I'll take the speaker and I'll take the speakers and press it through the embedding. I'll take I'll take the sentence and press it through the embedding 0 to create the sentence embedding. And then I'll take the speaker and press it through embeddings 2 to create the speaker embedding. Now what I'm going to do, this is the next piece of code that's a little bit different than what we've looked at. I'm going to create what I call embeds full, and that's the embedding of both the speaker and the sentence. So we'll concatenate them together. So we're basically making a vector of length 30 that will describe both starting with the speaker and then moving over towards the words that the speaker uses. That embeds full 30, which again is just the same as it is here. 10 plus 2 times 10 is 20, plus 10 is 30. 30 dimensions go in, it comes out as out. This is 128. 128 goes in, and 1 comes out. We run that through a sigmoid. Again, I haven't changed the variable names. At this point, you probably should tell me that I should have changed some of these variable names to make it a little bit more clear. But in this case, we're just still using the original variable names of log probs. Log probs comes out of the return. And this is all that's changed in terms of our code. So I want to really note what we've done. We've initialized 2 embedding spaces. And then all we've done is really form those 2 embeddings with 2 passes through and then concatenated the data together and then passed it through our neural net. Pretty straightforward. Now, things at this point should be largely the same. We have a loss function we'll have the losses, a list that we're going to keep adding to. We'll have the loss function, which again is the binary cross entropy loss, just like our last example. Then we'll generate this n-gram language modeler. Again, at this point, it's time to say, John, you should change the variable names for these functions, but I've tried to keep them the same so that they're clear. We'll probably change them for the next sample code. We'll take that speaker, we'll take the vocab, right? So the number of speakers, the length of the vocab, the embedding dimension, which is 10. Again, it's the same embedding dimension for both all the words in the vocabulary and for all the speakers, and the context size of 2. And that will form our model. At this stage, our model's been initialized, but no code has really been run. We've only gone through the initialization step. The optimizer will take stochastic gradient descent, passing in the model parameters. There's a certain value that's set there. Nothing interesting. Now our epoch, for each of our 10 passes, we'll train this total loss. We'll initialize a 0 for the total loss so we can see how it's continuing to rise. We're going to do the same thing. We will take the data, we'll take into the speaker, the sentence, and the target, right? So the 3 components. We'll take the word indices, which are the word index And this becomes a list, and we'll take this list and we'll pass it through the tensor to come back to the word indices. Perhaps this is not the best use of variable names, but I like this just because it's kept everything about the same. This represents the same thing we were working at the last time. I just like having this code a little bit sort of unnested the way that it was. Similarly, we'll have the speaker index. So in this case, we aren't a tensor. We're just this list of the speaker values, which of the speaker IDs it is. And then we'll turn that into a tensor. We'll zero out our grad. We'll run the log probs for the speaker index and the word index. Note that when we run this model, the speaker index and word index, this is what's coming in as inputs. Inputs has two values of speaker and sentence. So all we've done is take the speaker indices and the word indices and sort of bucketed them together in this tuple so that we can pass them through into the forward pass, and then we'll unbucket them, uncompress them here to these two spaces. And then what we're going to do is we'll come up with, again, I'm calling these log probs just because it's the same variable names, but we should probably change that. We'll come back with the recommendation, the value, the loss for how far away or what we think the sigmoid thinks is the more probable result given the speaker and the words that they used. Is it a compliment or is it an insult? If it's an insult, it's closer to 1. And we will take the target, the actual value, again, the target that's drawn from data. That's the empirical result, what we know our label to be. And we'll push that through our loss function. We'll take the loss and backpropagate the loss. We'll do an optimization step. We'll concatenate onto this list of total losses, which is here. We'll add the loss for this particular pass, for this step through this pass of the data. And then at the end of each epoch, we'll sum the loss, so the loss for each epoch, into total loss, and that total loss will be appended to our losses. So we're collecting along as we go down the path. So we can run all the way down to our print losses, and if we run this whole thing in one big go, we see that I ran into a bug. Probably this is because I ran it all too much in one pass. And now we see what our losses are. We see our losses start at 19.07, or excuse me, 04, and they are continuously decreasing. They're monotonically decreasing at each step down the line as we get down to 17. Now, it's worth noting that these numbers, to see our loss decreasing, doesn't tell us the accuracy of our model, doesn't tell us how well we'll do on unseen data. It just tells us that our model's learning. And that's really what we've been perhaps been a little bit lackadaisical here. It's more typical in tutorials to see the whole process of what we do for cross-validation, evaluate that our model is actually working correctly. We haven't dealt with any of those things to get to this point. At this point, all we're looking at is the mechanics of getting a PyTorch model up and running using the tools and libraries that are required. The next step, the next series of videos that we're going to be working on are going to be about expanding this and enhancing it. So the first thing I'd like to do is I'd like to set up a test and train set. We haven't touched on this. Test and train requires another block of code. It's going to be basically the same example that we've been working with above, but instead in this time what we're going to do is we're going to take an example perhaps from each individual speaker and hold that out and use that for the development set. So in a typical PyTorch scenario, you have the train, dev, and test. And what we're going to do is we'll just look at that train and dev to get a sense of how well our model's progressing. And ultimately, there's a great deal of similarity with the way you handle a dev set and a test set, so we won't worry about that so much. And that will give us a way of understanding if our model's actually continuing to learn on unseen data, or if as we train our model and we move forward, the model's overfitting and just really latching on to the data that we have. And we probably know, given the size and scale of our data, that our data will be latching on to just the data that we have. It will be memorizing our data set. 10 passes on 25 or 30 entries is a ridiculous quantity. But at the same time, it's really helpful to understand the mechanics. So once we get that next step, which is how we set up a development step, or the dev test, the dev training split, that'll be the sort of goal for the next video, and then we can decide where we want to go after there. So in the meantime, try to look around and see if you can find some examples of how you might do that, and give it a go. See if you can set up a dev set on your own. Speak soon.